Okay, a couple things I want to talk about. First thing I want to talk about is test one. Oh no. If you take a look on the syllabus, it says test one about here. And on the syllabus, basically that's just a marker, a reminder that, hey, we got to be talking about test one. I wanted to get this settled the other day, but with the egg drop and that stuff, didn't work out so great. So let's see, today is the 30th. Let's see, so this is going to be about 2, 4, 7, 9, 11. Now, what's the deal with class on the 11th? You don't have class on the 11th, do you? Why not? It's kind of right in the middle of the semester, and Thursday and Friday of next week. Okay, so next week, on this Thursday and Friday, it's what are called reading days. A number of years ago, the student council at UC said it is a long run from August all the way up to Thanksgiving without a break. And it would sure be nice to have a breather in there somewhere. And they came up with the idea of introducing what are called reading days. So it's a Thursday and a Friday where classes don't meet, and it's the proposed use for them is to get caught up, Austin's laughing at that one, is to get caught up on homework and get reading done and all that good stuff. Okay? What a lot of people do is just peel over in exhaustion and lay there for a day or two. But either way, regardless of what you're going to do with them, October 10 and October 11 are reading days in the university. Classes do not meet. Yahoo! And it's a chance to kind of get caught up, take a breather, maybe sleep past 5:30 or 6 in the morning. I'll probably sleep until 6, maybe. Okay? On those days, be a little lazy. Okay? But it's a day to get caught up on stuff, no classes. How about that? So we can't have exams on that day because it's not a class day. But what we can do is we can schedule an exam either or any of those three choices. I hate to put it off to the week afterwards because after having been off a bit and then come back and get hit with a test, that looks like a recipe for disaster. Okay? So I'm going to throw a few dates out there as possibilities. Friday the 4th, Monday the 7th, Wednesday the 9th. Hey, you're here just in time. We're getting ready to vote on the test. Okay? So a couple of options for test dates for test 1 would either be this Friday, Monday of next week, or Wednesday of next week. Now remember, you have Thursday and Friday off on next week, so we can't do it either of those. Otherwise, we've thrown in the 11th as an option as well. Okay. You get to vote once. If you don't vote, don't complain when it landed. Okay. Do you need to check your schedules or calendars or anything to figure out what else is going on in your life on these days? Or I like the, yeah.
So it's not during class time?
It'll be during class time. It'll be one of these days, but the reason I throw out the opportunity to choose a day is I don't want to just pick a day and find out that, you know, you've got a midterm in chemistry, you've got a speech due in English, you've got, you know how those days hit. Okay, I want to try and get the math test scheduled so it's not one of those days. And I don't know what those days are. You know what those are for you, and it gives you a chance to vote around those opportunities to do 17 things in one day. Okay? I'll probably remember till the day I die, the day that I had had finals in chemistry, physics, and A&P back to back to back. Had organic chemistry, physics, and anatomy and physiology. One after another after another. That was a fun 6 hours. Okay? Getting ready for it wasn't much fun either. Anyhow, now check your calendars, figure out what'll work, what won't work, all that good stuff. Okay, you ready to vote on which days? Okay, remember you only get to vote once. Oh, rats, it's not like Chicago where they vote early and vote often. What? What are you talking about, Chuck? Chicago is notorious for voter fraud. Did you know that? Okay. If you check in history, there have been dead people who voted 5 and 6 times in one election in Chicago. You don't want to hang around the cemeteries. They're really busy with people rising from the dead and zoom into various precincts to vote. Or somebody's voting for them somehow or another. Anyway, so you get to choose one of these 3 test dates. How many of you want it on Friday, October 4? That would be this coming Friday. Okay, so Austin gets his vote in. The next option is Monday, October 7. How many of you want on Monday? Well, so it looks like 1, 2, 3, 4. So the returns are increasing. Wednesday, October 9. Oh, we got some 2 votes there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 14, 15, 16. Looks like about 17. So it went up by about a factor of 4 each time. You just multiply by 4 and you get basically the next set of results. I'm sorry, Austin, it wound up landing way far from where. Okay, so your test 1, it looks like, is going to wind up on Wednesday, October 9. Let's do the cutoff for material as right here. Last new material. What that will allow for is by the last new material being on the 4th is you can do the homework over that weekend. Then if you have any questions, it gives you the opportunity to ask about it on Monday. Okay? Yes, sir.
I think it was after chapter 2.2, the part 1 and part 2, you gave 2 more homework assignments, but they were like due like the next day, and I don't think.
Okay. Yeah. Okay. What I'm going to wind up doing is to just send out an announcement, do these problems, and go after it in the book. Thank you for reminding me. Okay, so 2-3, 2-4, along in there. Let's see. I'll throw out 2-2 as well. Okay. Yeah. Thank you. Okay, so does that make sense how things will work? On Monday the 7th, is that going to be just a review day? No. If you have questions, I'll answer them. But if you don't have questions, I'll just cruise on with new stuff. Okay? Because I'm thinking, let's see, we've got 3 tests. Well, if we do 3 review days, we'll lose 3 days for tests, 3 days for review. How many weeks out of the semester is that? That's 2 weeks gone, isn't it? Which is kind of like a whole lot of time, more than what we can really afford to go after. All right. So there's that. On the egg drop, had talked about the prospect of doing it out here in the lobby area. And as I got sizing things up, I don't have enough rubber bands. Okay? And I wasn't sure if the rubber bands would take that much jerk or if they would break. So what I wound up doing is, if you've checked your grades, if you were one of the 2 groups that was closest, you all just got an 11. You all got the 1 extra point, if that's okay. And the folks who were in those groups that came like this far away. Okay. So I just gave everybody the extra point. I hope you're not bummed and thoroughly, gosh, Chuck, I wanted to see the eggs jump off of the balcony. Okay. But yeah, I got figuring out and realized I don't have enough rubber bands. And it would take the whole class, even if it did, for you to put them together. So I thought, okay, we'll go with plan B on that. When you were doing that egg jump, you came up with an equation, didn't you? Does anybody happen to recall about what their equation was? Or if you can look it up, that's great. Yeah.
Ours was y equals 5.75x plus 3.
X recall about what theirs was? Or were they kind of close to this one? Anybody have 13, 14, 15 for the coefficient on x? Got a bigger number? Okay. It's okay if your equation is different from this. We're just going to talk about them. It doesn't mean one's good and one's bad or anything like that. What let's do, okay, is figure out where these different numbers come from. When you drop that egg, you've got a series of rubber bands, don't you? And then off of that, you have the egg itself. There are two different parts to this system. The one is the rubber bands, which will change in length. And the other is from the top of the paper clip to the bottom of the egg. Did the top of the paper clip to the bottom of the egg really change? Or did it stay the same? The paper clip change? Did the paper clip stretch way out? That stayed pretty much the same length, didn't it? The egg, did the egg go and suddenly stretch down, or did it stay pretty much the shape it was? Shape it was. So this distance here was pretty much constant, wasn't it? And one of the things I asked you to do the other day was to measure from the top of the paper clip to the bottom of the egg. Logan, do you happen to have that measurement for your folks?
I'm not sure.
Okay, that's fine. It was what, about like that? Okay, so it's about 3 inches? Maybe a little more, maybe a little less. It's not 6 inches and it's not 1 inch. True?
Yeah.
Okay? Yeah, because 6 inches would be like that and 1 inch would be like that. The thing that's kind of neat about this project is the numbers in there, if you had the chance to measure from the top of the paper clip to the bottom of the paper clip, these numbers actually apply to different parts of your system. This constant in your equation should be pretty close to the length from the top of your paper clip to the bottom of your egg. Because remember, that whole equation on the right-hand side describes the total length, doesn't it? Okay, so it's going to be the whole length of your bungee egg. Well, your bungee egg has two parts, a part that's fixed, the part that changes. The fixed part is the egg length with that staple on it, or staple with the paper clip on it. Now, take a look at the other part. What does X represent? Wasn't X the number of rubber bands that you used? What would the 5.75 mean? It's going to be the number of rubber bands times the number plus another 3 inches tells you how long the thing stretches. Any idea what the 5.75 might mean? It's okay, throw an idea out there. The worst is it doesn't fit, and we'll hang it back up on the rack and look for something else. It's the slope, yeah. The slope talks about how much something is changing. In this case, it's talking about how much the, isn't it how much the rubber band changes? Stretches. That's right. That 5.75 there should pretty much reflect the amount of stretch in each rubber band. And if you think about it, that makes sense. Because if you put 5 rubber bands on, and each one stretches, say, 6 inches, the 5 times 6 is going to give you 30 inches when that thing hits the full extension. And then you're going to have another 3 inches down at the bottom, aren't you, for the egg with the paper clip. Does that make sense what's going on with this? It's actually kind of a fun little project because it allows you to take a look at what's going on with each part of the equation, and it comes back to something that you were actually working with the other day. So it winds up happening here. The constant part reflects the constant length of the paper clip in the egg. The variable part represents how much each rubber band stretches, and as you add rubber bands, you get a longer stretch, don't you? You look thoroughly excited, or worn out from the weekend, something or other. Okay? But that's what's going on with that. Okay, before we did that, last Wednesday, I'm hoping you had some fun with that. I don't know if any of you have ever done that before or not, but it's kind of cool. It's kind of fun. Okay, I was really impressed. Nobody killed their egg on the jump. No eggs died in the jumping. 1 or 2 before the jump, but none during the jump. That's okay. Okay, what we were talking about last time was things like piecewise functions. If you'll recall, with piecewise functions, they graphed something like this. You remember this? What's an example of something that you've encountered that would be a piecewise function?
Well, you mentioned the hurricane.
Yeah, the wind speeds on a hurricane determining what level of hurricane it is. Is it a level 1, a level 2, a level 3, a level 4? Okay? As soon as it hits a particular wind speed, it jumps up to the next level, doesn't it? Then to the next one. Okay? So that's one of those things that will produce this stepped effect. Another one is like shipping. If it's within a given weight range, they charge the same amount of money. And then if it gets to another weight range, they charge a different amount of money. And on up like that. So what winds up happening here is there are quite a few things that you encounter in the real world that really are stepwise functions. You just may have never thought of it like that before, okay? But there are quite a few. Are you okay with those? I know this is a real quick comment on it today, but that was from before. Another thing we talked about was the greatest integer function. And this is about where we left off last time. It has kind of an unusual notation. It goes something like this. It looks like brackets with 2 backs on each of the brackets. And what this does is it returns the value of the integer of that number, the integer part of that number. So for example, if you have something like y is equal to the greatest integer of 4.107, it returns the integer part, which is 4. If it's something like y equals 5.968, what integer value is it going to return? 5. It just pulls off the integer. And we talked about the idea that something like this would be handy if you're talking about production. It's one place that would come into play. So for example, it's Friday afternoon, place shuts down for the weekend. There are products on the assembly line in process, but can you sell those just yet? No, because they're not ready. It's a microwave oven without a door on it. Yeah, that's going to sell really well. Okay? It's a TV without whatever, fill in the blank. Okay? It's still missing the back of it. Okay? And the question is, how many total units do we have available for sale? Well, you've got the whole number, the ones that are complete units, but then you have some pieces of other units, but you can't sell those. Okay? So that winds up giving you then what's going on as far as total units that you can sell. Okay, so that's what we talked about the other day. What we're going to dive into today, rats, I forgot what section this is. I forget if it's 2.5 or 2.6. 2.5. Okay, in section 2.5, we're going to talk about absolute value equations. Okay. An absolute value allows you to measure a distance. What's the distance basically from Cincinnati to Dayton? No, about 50 miles, something like that. It's about an hour drive. Okay. I'm guessing, but probably somewhere around 50. Somebody could probably pull it up. Hey Siri, how far is it from Cincinnati to Dayton? You know, or Alexi. Just be careful, don't let Siri and Alexi get in a fight. Okay. So, but the point is, if the distance from Cincinnati to Dayton is 50, what's the distance from Dayton to Cincinnati? 50, right? And you don't worry about which direction you're going, do you? The distance is 50 either way. Well, what absolute values do is they look at and give you what is the distance without getting concerned over, are you going from north to south or from south to north? Are you going from higher to lower or lower to higher? Okay. All it does is it gives the number. Okay. So absolute values, if you'll recall, are kind of like that, just two tall lines. And an absolute value always gives you an answer that is positive. So these values are always going to be greater than or equal to 0. Okay. Does anybody recall what the graph of, now, hey, let's try this. Woo. Wow. Huh. Interesting. Just an experiment. I don't know how well it worked, but there we go. We'll see what happens. Okay, so now I can move it around. And maybe I can delete it. Yep. Okay. No, I don't want that. I want this. Okay, so rats. Oh well, we'll go with something like that. Absolute value. Does anybody recall what that looks like? You're okay. Yeah. It's like a V. Yeah. So it looks kind of like, well, it's not letting me write, is it? Apparently this graph erases. It looks like a V. This is y equals the absolute value of x. One of the things to notice about this is the graph never goes below the x-axis. Why not? Yeah, all the y values, everything that comes out are going to be 0, they're going to be positive. So you wind up with a V all above the x-axis, or just touches the x-axis there at the vertex. Okay. And what we can do is we can look at, how do you graph these things? Okay. So if you have something like y equals the absolute value of x, let's say plus 3. I'm not sure if that shape worked out as great as I wanted it to, but I guess we'll try it again, see if we can do something or other. Okay, if we do something like this, y equals the absolute value of x plus 3, where the plus 3 is on the outside. How do you go about graphing something like that? Well, the way to graph it is you first start out with your basic graph, and the basic graph shape is absolute value of x, isn't it? Okay, so we could do our first graph like this. Y equals the absolute value of x. Then from there, next thing we're going to do is throw in whatever's also included with it, the plus 3. What's that plus 3 going to do to each of the y values? It's going to move it up 3, isn't it? It's going to add 3 to whatever it was before. So before, if it was 0, now it's going to be 3. Before, if it was 2, now it's going to be 5, and whatever. So what we could do then is we can say, okay, it's going to move everything up 3. An easy way to keep tabs of what we're moving is to work with the vertex and just move that up 3. So I'm going to move the vertex up to there and leave everything else the same. And we get y equals the absolute value of x plus 3. Another change that can happen with these is okay to scroll on up a little bit. Another change is if you have something like this. Y equals the absolute value of x minus 2 plus 3. In this case, the minus 2 is on the inside. Let me see what other shapes they have. I guess that's it. Okay, how do you graph something like this? Well, we're going to do it step by step. No multitasking. First thing is, what's the basic function that we're working with here? It's absolute value, isn't it? So the first thing is going to be to say, okay, well, basically what we have is an y equals the absolute value of x. So there's that. And what we're going to do is we're going to add one feature after another and adjust it a little bit as each feature is added. So on the next graph, I'm going to do y equals absolute value of x minus 2. I'm going to save that plus 3 for a little bit later. On the x minus 2, this adjusts where y comes out as 0. What x value do we need to plug in to get a y value of 0 out? Well, try it. If you plug in 0, you're going to have 0 minus 2. That's okay. No, that's not it, huh? Do you buy that x equals 2 is going to give us back a y value of 0? Does that make sense to everybody? Well, what that actually does is it takes whatever our graph is, it moves it so that the vertex is at x equals 2. All that is done is to slide the graph 2 units to the right. What do you think it would have done to the graph if you would have had y equals the absolute value of x plus 2? Shift it to the left, because then you would need a negative 2 to add to the plus 2 to get 0, wouldn't you? So the question whenever you do this particular step is, what x value do I need to plug in to get 0 out? Does that make sense? Yeah, I'm going to take the vertex, the nose of the thing, and slide it over to 2, the x value that gives us a y value of 0. Okay. Yeah, which 2? It's going to be the 2 that we plug in here. The 2 that you plug in there will give you a y value of 0. Yes, sir? It's good? Right, or 0.
X plus 2 in absolute value, does that mean still x plus 2?
Well,
because coming out of that, the reason that's on the right side of the axis is because absolute value is always positive.
okay, now, being on the right right or the left side isn't what makes it positive coming out. Being above or being below is what makes it positive coming out. Does that help any? Yeah, because remember, coming out.
It's still just confusing because if you're not,
Okay.
if there's no graph involved and you're just solving that equation, coming out of the absolute value would be x plus 2.
Not really.
Isn't that what absolute value means? That there's two bars on the
I see what you're saying. What we're going to want here is, let's take a look at that. You're thinking the x minus 2 has to be something positive, doesn't it?
Well, it's inside the brackets. Yeah.
Right. So let's put a marker here. Has to be positive. Or do you buy that it could also be 0?
I mean, if x is 2.
Yeah. Oh, look at there. For it to equal 0, that means x is going to be 2.
So you're saying you want it to equal 0.
Yeah. Yeah. Okay, so what happens first is you look at what's going on inside, and you want to figure out what's going to make this thing 0. And that's going to slide you left or right. Then, the next graph you look at is going to look at, okay, we're over here at x equals 2, but what we're going to now do is take an extra piece and tack it in. What does the plus 3 do to the graph? Well, it raises it up, doesn't it? Because any y on the right side, any y value that comes out of that absolute value is going to have 3 added to it. So if 0 came out, what's going to happen to 0? It's going to get 3 added to it, isn't it? Which is going to make you go up 3. Now the graph's like that. Please? Okay. So let's take a look at this. We're going to do it one step at a time. The first step is we start out with that. We know the basic shape. And the vertex is at 0, 0. Now the vertex can slide left and right. It can slide up and down. The first thing we're going to do is see, does it slide left or right? Left or right means it's still going to be on the x-axis. If it's on x, what's the y value? It's 0 because you're not up and you're not down. Okay, so if you're sliding left and right, the x value is going to change, but the y value is going to stay 0. So the question then is, where do I get 0 out Well, let's see. We get 0 out if x is 2. What happens if x is negative 2? Try it. What happens if x was negative 2? Could you plug it in there? Just experiment. It'd be 4, wouldn't it? It's not going to be 0. It's going to be way up there, isn't it? So the only place where this equals 0 is if x equals 2. So, and that's this x equals 2 is what gives us, well, that's kind of an awful looking arrow, isn't it? Got worse the more I tried to fix it. Oops. X equals 2 is the value you plug in to get a y value of 0 as a result. Does that make sense to everybody? Then, the next step, and we're just adding in one feature of the function at a time. We're going to put in the plus 3. Well, at this point, we're adding 3 to the y value, because that whole right-hand side is the y value. We've already figured out where can we get a y value of 0. And now what we're going to do is figure out, well, gosh, if we got just a constant thrown in, what's that going to do? It's going to take everything and shift it up 3. So that takes your whole graph and shifts it up 3. Let's do another one. Let's say if something like y equals the absolute value of x plus 3 minus 6. Okay, so what's the basic function here? Let's graph this. Basic function is absolute value. You buy that? So there we go. There's the basic function, absolute value. Next thing we're going to do is we're going to pick up a little feature. That feature is going to be the plus 3. Now the question is, what value of x do we put in there to get 0 out? And the reason we want 0 out is because we're interested in the vertex. We're interested in the nose of that. Where does this thing have a y value of 0? Well, it has a y value equal to 0 if you plug in what value of x? Negative 3. Which means that if we come over 1, 2, 3, this is where the y value is 0. Does that make sense? So here's the graph now. Okay, so now what? Well, the next thing to do is to throw in the next feature of the equation, which is a minus 6. What's a minus 6 going to do to every value that comes out of that absolute value sign? It says get whatever number you're going to get, and then what do you always do with it? Subtract 6. So what's that going to make or do to the y values? It's going to bring them down, isn't it? It's going to subtract 6. So wait a minute, we're going to come over 3, just like we did before, because we still have this plus 3 inside the absolute value, and the minus 6 is going to say, hey, we got to go down 6. There's that, and then you do your absolute value. Does that make sense? Huh, okay. When you're graphing these things, first thing, you look at what's happening inside the absolute value. Second thing, you look at what's happening outside, what's being added or subtracted. Now, there's one other thing that can happen with these, and that's, well, what if we have something like y equals a negative 2 absolute value of x plus 5 minus 3. So if we put a lead coefficient, or in other words, a coefficient out in front, well, what's that do? Well, the first thing is you start out with the basic function, absolute value of x, well, that's just this v. Are you starting to get the hang of that one? Okay. Yeah, the base one. Then from there, we're going to add in a feature, and the feature we're going to add in is whatever's going on inside of the absolute value. Okay, so when we do that, what we want to know is when does this equal 0? And that's right, at negative 5. So if you plug in a negative 5 plus 5, what's the y value? 0. So if we go to negative 5, that's where our graph hits the axis. Does that make sense? Now, the next thing we're going to do is we're going to drop in that 2. And consider what that does to the graph. Hey, what's that 2 going to do to every y value? Yeah, there is a negative coming in a minute. You're absolutely right. Thank you. Yeah, we're going to do this as 2 little separate chunks. First, we're just going to do the 2 and say, What does the 2 do to the y value? If it was 3 that came out when you multiply it by 2, what do you get? 6. If it was 5 that came out, now you get 10. Do you see it's going to make the y values big faster? What's that do to the graph? Makes the graph bigger. It's going to have steeper sides to it because the y values get big faster. Does that make sense? Instead of being, for example, 3 over here, it's now going to be up at 6. Instead, please?
Did the 2 not change anything?
Well, it's kind of hard to tell on these spectacular graphs that I make. But what's going on is it makes the sides steeper. It makes the V skinnier. Yeah, the V gets skinnier. Maybe we could even see if we can get this to erase these. Let's make it more extreme. There. Does that look skinnier? Okay, so what it does is it makes it skinnier because those values are getting big faster. Now, as was very quickly and absolutely correctly pointed out, is wait a minute here, that's not just 2 in front of there, it's a negative 2. So we looked at the 2 makes it skinnier. What's the negative going to do to all the y values? It's going to make them negative. So instead of the thing going up, it's going to go down because all the y values are going to be going down. It's still going to be skinny, but it's going to be skinny going down. Make sense? One last thing to do here. Take a look at this. On this function, way over to the right, we did what? Subtracted 3. So when we throw that in, that's going to give us y equals a negative 2, absolute value of x plus 5, subtract 3. Okay, so we've got a graph, comes over 5. And we know it's opening down, but what's the minus 3 going to do to every y value? It's going to make them all go down by 3 units, isn't it? So if it started out here at 0, it's going to now wind up down there at negative 3. Still going to have the skinny sides. Still going to open down. Variety of steps to this, aren't there? Now, one of the things that's really cool with this is once you get used to it. Let's say we have something like y equals a negative 1/2 x minus 5 plus 7. This doesn't happen the first time you do 2 or 3 of these. But after a while, you can kind of get the hang of this and say, you know what? The vertex is going to be over at 5. It's going to be up 7. So there's the vertex. The negative means it's going to open down. And what's the 1/2 going to do? Is it going to make the y values get big faster or more slowly? More slowly, so it's going to spread it out.
So when we have like our exam and stuff, are you going to be looking for all the steps when we write on our problems or no?
Whichever way you can really do it. Now, definitely want this labeled. This is going to be the point 5, 7. Now, there's a danger to not showing all the steps and just doing this. What's the danger? If it's wrong, what do you have in the way of partial credit? Whereas up here, if it's wrong, do you have any partial credit to fall back on? Well, take a look there. 1, 2, 3, 4, 5 graphs. Do you figure somewhere in 5 graphs there's got to be something worth a point or two? Yeah. Okay, so if you choose to just draw one graph and say, ta-da, there it is. Okay, you're putting all your eggs in one basket, which means the whole basket's either going to be okay or the whole basket's going to crack, one or the other. If you spread it out like this and say, here's the first step, here's the second, here's the third, and I can see step by step what's going on. Even if you mess up one step, you get credit for all the other 4 steps. So you get 4 out of 5. Yes, sir.
How many steps do you use 2 or 4 or 5 steps?
Well, on this one that we're looking at now, there was one step here. Here's the second step. Here's a third step, a 4th step, and a 5th step. So this one would have 5 steps to it to account for the absolute value, to account for the plus 5, to account for the multiply by 2, the negative sign, and the minus 3. So you're accounting for each thing one piece at a time. Whereas down here, it's all in one step, isn't it? It's a do or die. Those can be fun depending on how much of a risk taker you are, but remember there's nowhere near the opportunity there to go after any partial credit. All right. Let's take a look at one of these things. Let's say we have something like y equals the absolute value of x minus 3 plus 4. And the question is, where is y equal to 0? What values of x will give you back y equal to 0? Now this gets kind of tricky because what that's really saying is solve this equation for 0, isn't it? Which also means that the absolute value of x minus 3 equals negative 4. Looks like Austin eyed me suspiciously for just a moment there. What's the problem with this? Anybody? It can't happen, can it? Can the absolute value equal a negative? So here, the correct answer is no solution. I've mentioned to you before that mathematicians don't like to use lots of words. It's a contradiction can also be written like that, where you have an x and 2 little x's on it. Now, what if we change this a little bit? We said y equals the absolute value of x minus 3 minus 4. And now you're asked, where is y equal to 0? Well, this would give us the absolute value of x minus 3 minus 4 equals 0, wouldn't it? Is that looking better? Well, let's see. That means the absolute value of x minus 3 equals 4. Is that legal? Now, one of the things to realize is the stuff inside here. The stuff inside could have either been a 4 or it could have been what? Could it have been a negative 4 inside of the absolute value? Is it legal to say the absolute value of negative 4 equals 4? Is that okay? Oh, okay, yeah, I guess so. When you get to this point, you can go 2 directions. you can either say, well, gosh, this x minus 3 could equal 4. And if you get 4 inside the absolute value, that'll work. But you could also say, you know what, this x minus 3 was a negative 4. Does that make sense? Now, how many things do you have to solve? How many equations do you have to solve at this point? 2 of them, don't you? This is going to give us x equals 7. What's the other one going to give us? You see it's negative 1. Is there any way you can check to see if that's correct? Yeah, plug them in. So, yeah. So what we can do is we can say, okay, we have this absolute value of x minus 3 minus 4 equals 0. There's what we want. So let's plug them in and see what happens. Absolute value of 7 minus 3 minus 4, does that equal 0? Yeah, that works, doesn't it? The other option is to say, okay, I'm going to plug in the negative 1 minus 3 minus 4 equals 0. Man, there are all kinds of negatives floating around there. What's the minus 1 minus 3? Negative 4. So we have the absolute value of negative 4 minus 4. Is that true that that equals 0? Yeah, because absolute value of negative 4 is 4. So that gives you 4 minus 4 equals 0. Does that make sense to everybody? How could this have 2 values where it's 0? Yeah. If we take this and graph it, pretend that's a vertical line. If we graph this thing, it first means we're going to slide over 3 spots, correct? So that's going to give us this. Then what's the minus 4 going to do to the graph? See this negative 4 outside here? What's that going to do to the graph? Isn't it going to bring it down? So it'll come down 4. 1, 2, 3, 4. And when we do that, you're going to get something like this. And it's going to intersect the x-axis here at x equals negative 1. And it's going to intersect over here at x equals 7. Everybody good with that? Does that make sense? And if you'll look, see it? There's your 7. There's your negative 1. Those are the 2 solutions. So realize it's possible to get more than one answer with this because it's intersecting the x-axis in a couple of places. Okay?